All right, so I'm going to pick up where I left off. Someone came in for my office hours, so I had to stop it there. But I am going to finish this now, this review for the OChem 2 final. So I'm just going to completely start over on this question. So honestly, when I look at these, a question like this, if I don't know the name of this right away, I'm going to start from the names that they give me. So aniline, I remember, is NH2, and then if there's an ortho, then the bromine would be here. Just remember it's ortho. Meta, the bromine would be here, and para, the bromine would be here. So if our NH2 is down and our Br is up here, that's meta. So just remember ortho, meta, para. Every time I'm always thinking ortho, meta, para. So between these three, ortho meta looks right for now. It's definitely not ortho. Those two groups are definitely not ortho to each other, and those two groups are definitely not para to each other. So even if you don't remember for sure if that's aniline or not, then that's how you can eliminate that. You can also eliminate D because you know they're not ortho. And then is it 1, 2, 3? They are 1 and 3 apart, but we did not learn to say amine ever just at the end of the amines for the benzene ring. So that's not an option either. But even if all you knew was that these were meta, you could at least get it down to just being a potential of A and E. So that's again what I mean when I say use what you definitely know to eliminate wrong answers. You could at least have gotten it down to A and E, and then you would just have had to decide which one of those seemed more right. And aniline is one of the names for the benzene rings that I had you memorize. So make sure that you go back and look over those and know those common names. Okay, the next one, this is electrophilic aromatic substitution. If you're ever not sure what reaction is going to happen, I also forgot to say this, but I'll go through the list of like what reactions did we learn. So this semester we did, let's see, I think the first we did was Diels-Alder. And then we did electrophilic aromatic substitution. We did alcohols, so adding alcohols across the double bond. Reactions of alcohols and ethers. And then we did, let's see, after that we did oxidation reduction. And then we did carbonyls. So when I look at this, there's only thing that it could be is electrophilic aromatic substitution, because electrophilic aromatic substitution requires an aromatic ring and none of these other ones do. So when I see these two things, I'm like, oh, this is going to be electrophilic aromatic substitution, which means it's going to add the nitro group. And it adds the nitro group as NO2. So even if you don't remember for sure what it looks like, you can at least get rid of all of these, and then you can narrow it down to these two if you just know that it's electrophilic substitution and it adds the nitro. The NO2, I made y'all draw out what the electrophile looks like and how it gets to NO2, so you can go back and look at the mechanism for that. Okay, next question. What is the major product of the following reaction? This is a Friedel-Crafts acylation. So again, this is a type of electrophilic aromatic substitution, and I know that based on the fact that we have a benzene ring here, and then we have an acyl group and a Lewis acid. So for electrophilic aromatic substitution, you usually need some kind of acid, you need an electrophile, and you need an aromatic ring. So we have all of those here, so I know it's going to be electrophilic aromatic substitution. And then the question is, which side is it more likely to react on? Is it going to, you have to think about like, where will the substituents direct it to? So this is when we talked all about the ortho-para directors versus meta directors. And basically we have two separate benzene rings, and one has a CH3, which is an electron donating group, and the other one has an acyl group, which is an electron withdrawing group. And since your since your benzene is the nucleophile that attacks the electrophile, you want this to be more nucleophilic. The more substitutions it has, the more reactive it is. And so it's more likely to react on this side with the electron donating groups because the electron donating groups are better. So when I look at this, I think this electron donating group is a better option. So it's more likely to add on that side. Now the other thing is electron donating groups are typically ortho-para directors. So it is very likely to either add to the ortho position or the para. So ortho's here, meta, and para. So it could add to one of these two ortho positions, or it could add to the para position. So I'm going to first eliminate anything that adds on the side with the acyl group first, because we know that that doesn't have the electron donating group on it. So it can only be one of these two. And this is ortho meta. This is meta, and we said it would be more likely to go para. So ortho meta para. So that's how we get to answer choice E. Okay, next question. Which of these structures contributes to the resonance hybrid of the intermediate formed? So let's see. If we have bromobenzene is going to go through ortho meta para. So it would add here. The chlorine would add here. We'd have the bromine, and then the electrophile adds here. If you don't remember this, I do have a short video on electrophilic aromatic substitution. It's like under 3 minutes, I think, so you can look on my channel for that. It's like, I think I broke up some TikTok shorts and then I put them on YouTube. So then this goes over here, and we get the Br still here with a positive charge, and then your double bonds here, and you have a double bond here, and your chlorine, and then we go here, and we get the Br with this and this, the chlorine and the positive charge here. So those are all the different resonance structures that I see. So let's see. Oh, and then there is one. So I'll just first check for these. This one right here, where the positive charge is right on the Br, we have A. B, we haven't done that yet. I'll come back to that. C, that's the first one we started with right here. This one, where the carbocation is right there. So we have that one. And then right here on D, we have the carbocation right there. We have that here, so we have that structure as well. So just based on that, we have A, C, and D. So probably E is going to be your answer. But I didn't draw this one. Sometimes I forget to do this one. There is a resonance structure from this one where this goes down and fills in that positive charge, and you get to the Br being positive. And I just missed it. So seeing that made me realize, like, oh, yep, that one's there too. I just didn't think of it. But I would have been able to get to the right answer even without remembering that one for sure. Okay, next question. Propose a series of reagents in the proper order to accomplish the following transformation. Okay, so this is, remember when we did electrophilic aromatic substitution and we talked about electron withdrawing groups versus electron donating groups. And you had to decide if they were going to be, what order they were going to go in to make sure they would donate. But also, we had to learn about primary attachment of alkyl groups. So, from here, I know we've done 2 steps. One is nitration. Also, if you weren't sure on that nitro question earlier, if it was NO2 or NO3, here's a little hint for you on how you know. So you can also, that's a test taking tip, is if you're ever not sure, look for other questions that ask similar things. Okay, so the first step would be HNO3 and H2SO4, or that's at least one step, I guess. I won't put them in particular order yet. That would add a nitro, and this would be a meta director. But this is extremely deactivating, so it's not going to be super happy. It's possible for this to react, but it's not going to go really well. But so just keep that in mind. The next thing we would do would be to try to get this added on. But if you remember Friedel-Crafts alkylation, they have to form a carbocation. And primary carbocations don't last, they'll undergo rearrangement. And so if we did a primary carbocation like that, the thing that would add would look like this. That's not going to work. So what we talked about instead was doing a Friedel-Crafts acylation, where if you do a acyl group with AlCl3, that will add on, still in the meta fashion, your acyl group, and then you could do, I think it's zinc chloride and, or is it zinc and mercury and HCl? This will be a multiple choice. I think it's zinc, mercury, and HCl, something like that. And that will be your reducing reagent. And so you get your reduction, and then this basically, what this reagent does right here is it just eliminates this. And so it gets you to your primarily attached alkyl group. So we did a lot of questions like that. And so this will be a multiple choice question that would come up something like this. And so you just have to know that you would have to add the acyl group before you do the reduction. This has to happen first and then this second when these two are paired together, because you can't reduce something if you don't have the acyl group first. You could do the nitration first, or you could do this first, then the nitration, and then the reduction third, because you have to keep it as an electron withdrawing group whenever it's going to be, whenever it is, if you put that on first. So if you, for example, if you did first the Friedel-Crafts acylation, and then you get this, and then you reduce it with the zinc, mercury, whatever, you end up with this, which is now an ortho para director. So then if you did a nitration after that, it would look like this. And that's not what you want. You want them to be meta. So you could insert the nitration here and then do the reduction. It doesn't matter. But I think, like, if you have a multiple choice question like this, I've used a multiple choice question like this before, as long as you knew that this had to come after this, you would be in good shape. I don't know why it just saved my PDF like that, but okay. Next question, we did this one together in class, but arrange the following compounds in order of decreasing reactivity and electrophilic substitution. So if we have a benzene ring, this is sort of our standard. If you have anything with electron donating groups, that makes it more reactive. Just like I mentioned before, the reactivity, it'll attack first, so it wants more electrons. And then if you have anything with electron withdrawing groups, this is less reactive. So I give you a list of things that you should know and the relative reactivity of them, but if you can remember, like for example, nitro has a positive charge, so this is a strong electron withdrawing group. So that means this is not very reactive. It could react a little, but it's not very. Methyl donates electrons, so this is mildly electron donating. And so I just sort of go through like this, knowing acyl group has that resonance structure where this is partially positive, so this is mildly electron withdrawing. This is strongly electron donating because it has those resonance structures. And then halogens are sort of an exception. So even if you can't remember halogens, if you could just do this, knowing that this nitro is very strongly electron donating, that is the least reactive. So just knowing that is their order decreasing, so most reactive first. So I can eliminate A and C just knowing that this is the least reactive. And then if I know that this is strongly electron donating, at least know that it's more strongly electron donating than just plain methyl, then I can get rid of A. And C is all that's left. So even if you just knew that this was strongly electron donating, then that would get you to the right answer. So, and if you just knew the basic concept. So again, that's what I mean when I say use the things that you already know. Okay, this substituent deactivates the benzene ring towards electrophilic substitution, but directs it towards orthopara. So electron deactivating or electron withdrawing, but still orthopara. That's an exception, and that exception is halogens. And the reason for that is they are very electron withdrawing because they're so electronegative, but because they have these lone pairs, they're able to make a resonance structure that adds electron density. So they're just kind of like a paradox. Okay, so the next question, question 39. What is the correct IUPAC name for the following compound? Okay, so this is a ketone. And the very first thing I'm going to think is, we know it's a ketone, so it ends with one, not known. Ends with O-N-E, so you drop the E and add O-N-E for ketone. We never learned to just use the word ketone, so I'm immediately going to get rid of D. And now all these, there's heptanone, octanone, so if I can decide if there's 6 or 8 in the parent chain, that will help me out. So I'm going to go ahead and number this. 1, 2, 3, 4, 5, 6, 7, 8. So it's not going to be heptanone because that's 7. So it has to have 8. So it's one of these two. So now if you can just decide between these two, what is it going to be? Well, both of them have 4 own. So we've decided that the parent chain is octane. You're going to drop the E and make it octanone, and the position of the octanone is octan 4-one. So both of these are the same, or you can also do 4-octanone. Either of those is correct. So then we just have to decide about the substituent. So do you know if you can count to 8, and if you know that we don't have the word ketone in the nomenclature for ketones, you've already narrowed it down to just these two, and then can you name the substituents? Well, if you can name that this substituent is a methyl group, then that should be that. And the reason I know that's a substituent is this whole thing is the parent chain, so only the things coming off of it are a substituent. So this and this is coming off of it. So our only substituents are the octanone, is the ketone, and then the methyl. Isopropyl is a group like this. Is a group like this off of your chain, and we don't have that, so it's kind of like a trick. All right, what is the correct structure for 3-phenylpropanal? So if you remember that on is for ketone, al is for aldehyde. So propanal, propane, if you drop the E and add Al, that means that it's a propane that's an aldehyde. So we have 1, 2, 3 carbons. And then the last carbon, or the first one, depending on how you write it, but at the end of the chain, you have to have the aldehyde because the aldehyde is automatically going to be at the end of one of your chains. So this is the first thing I think is like, okay, so now we have our 3 propanes. I'm not sure about the numbering of this, but we have 3 carbons, and then at the end of it is the aldehyde. So that's what I'm looking for. And then it's 3-phenyl. Well, the aldehyde part is the higher priority, so we're actually supposed to start numbering at the aldehyde. So 1, 2, 3. So right here is going to be our benzene ring. That's what phenyl stands for. So make sure you know the difference between phenyl and benzyl. Benzyl has a bend in it, so it would look like this, and then your chain, whereas phenyl is directly attached. Okay, so looking at these, I'm going to immediately get rid of anything that doesn't have an aldehyde. So just from knowing that Al is aldehyde, we can get rid of this, we can get rid of this, and we can get rid of this. So if you know nothing else except that Al is an aldehyde, you can already narrow down your answer choices to this and this. And then if you know that propane is 3 carbons, which hopefully you remember, Mama eats peanut butter, and I do have a video on nomenclature if you need to watch that. M is for methyl, so that's 1 carbon. E is for ethyl, so that's 2 carbons. P is for propyl, so that's 3 carbons. And B is for butyl, so that's 4 carbons. So if you just know that propyl is 3 carbons, between these two, this has 3 carbons, or that has 2 carbons, and this has 1, 2, 3 carbons. So the one with 3 carbons is the right one, so that's answer choice E. And I actually drew it wrong here, where I drew it. I lost one of my carbons. On the 3rd carbon is where the group should be attached. So it should look like this. So I actually drew it wrong initially. 1, 2, 3 carbons. So answer choice E should be the right answer. Okay. Next question. What is the predicted product of the reaction shown? PCC is an oxidizing agent. It's a weak oxidizing agent, so it cannot oxidize past aldehyde. It can, though. It can oxidize primary or secondary. If it has a primary alcohol, it'll take that to an aldehyde. If it has a secondary alcohol, it'll take that to a ketone. So I see a secondary alcohol and assume this will become a ketone. And I see a primary alcohol, and I assume this will become an aldehyde. So that's what I'm looking for. So it can't be this because PCC is a weak oxidizing agent, so it can't go all the way to carboxylic acid. It can't be this because secondary alcohols can't become aldehydes. 2 carboxylic acid, so I'm going to get rid of that, and I'm going to get rid of that too. So that leaves me only with this answer choice. So if you just know that PCC can't get you all the way to a carboxylic acid, you could have gotten rid of 1, 4, and 5, leaving you only with 2 and 3. And then as long as you know that secondary alcohols go to ketones, then you would have been able to narrow it down to answer choice 2. Okay. Excess O3, what's the prediction of this? Excess O3 is, that's one of those where ozone, I just know immediately that ozone cleaves. And then the second part, dimethyl sulfide, this is just a solvent. So ozone is going to cleave, and it does not add a carboxylic acid unless you have H2O2 or water or some other source of oxygen. So it'll stop right here, and it just adds an oxygen here and here is how I think of it. So the rest of it looks the same. See how this looks just like the ring that we already had, and then I just draw on my hydrogens because it's easier to see. So that's what we'll get. So these are 1, 2, 3 carbons. So it would have cleaved this bond too, so that one's not correct. I think there's something I'm hitting with my sleeve to make it do that. It would have cleaved this one too, so that one's not correct. This one, I don't even know what happened, so definitely wrong. This one, this is what it would have been if it only had cleaved on one side. If it only had a double bond right there, but it had 2 double bonds, so we end up only with E. Okay, and that is going through each one and knowing why the wrong ones are wrong, and why is this not right, is because it's not cleaving the double bonds, or, you know, being able to process through like that is really important, because I'm not going to be asking you these same questions on the exam. I'm going to ask you just these same concepts. So be sure that you know why and that you've really thought about all parts of the question. Okay, next question. Which of the following compounds is least reactive towards a nucleophilic addition reaction? So a nucleophilic addition, that is the one with the carbonyl and the nucleophile adds, and you get O minus. And so, and your nucleophile is added. So your nucleophile is going to be attracted to a stronger partial positive. So less electron density, less electron donating groups is better. So this aldehyde is more reactive than a ketone, because these hydrogens aren't really donating very much at all, whereas these are donating more. I'm looking for an aldehyde. When I look at the aldehyde, let's see. I think all of these are aldehydes. So then you have to think about which one is donating the least electron density. And this is kind of a tricky one. My thought process is actually that the carbocation here is going to be more stable because of this. If we have, I know it might feel like this is adding electron density here, but in all of them we have a resonance structure where this becomes negatively charged, and you have a carbocation here. And for all of these without resonance, if we had less electron density, then that would be more nucleophilic, and it would be less sterically hindered. But I think I'm drawn to this one right here because I think that the carbocation would be more stable. So my answer would be A. There is a slight possibility. I didn't come up with this question, and there's not a question exactly like this on your test. There is one where it's like reason through which one of these would be the most reactive. But there is a possibility that this one, answer choice B, could also be because there's very little steric hindrance. So for me, it's down between A and B, and between A and B, I like A a little bit more just because I think that the resonance structure would stabilize that carbocation. But in general, I just want you to know that the less steric hindrance, the better. So like between these two, if I was going to rank them, this one would be more reactive because it's more electrophilic here. And that the less steric hindrance and the less electron. So between these, this one then would be the best between these two because there's no steric hindrance and there's less electron donation. Okay, what reagents are needed to carry out the conversion shown below? So this is kind of like a retrosynthesis type question where I'm thinking we started with a ketone and it became an aldehyde. So typically that means a nucleophile attacks and kicks this up and we get O minus, a nucleophile, and then whatever else was on the other side of your ketone. And then we add acid to get to this being an OH. So that's what I'm looking for. I'm looking for some kind of nucleophile that will attack. So the nucleophile that we need, it looks like it's O minus with this on it. Now we've talked about how this could be base catalyzed, but we could also do the acid catalyzed version, and it would just need to be deprotonated. So if we do acid catalyzed instead, the first thing that happened would be the ketone would protonate, and then we would get a resonance structure where we have OH plus, and it would be able to go up, and you would get a resonance structure with, sorry, my handwriting is so bad, OH, and this would be positively charged, and then even a weak nucleophile like alcohol, HO, this would attack here, and then you could get you would get the protonated version where it looks like this. Oh, this one should not be, sorry, this is not a benzene, it's just a plain alcohol. So then you get a protonated version where it's OH with OH plus and the cyclohexane, and then here we have and then you would just deprotonate that, get rid of this to get your final structure. So you could either have base catalyzed or acid catalyzed. So that's what I'm looking for, is base catalyzed. But if we do have acid catalyzed, if you remember, reaction with alcohol, that will keep going. This first addition makes a hemiacetal if you add alcohol. So to stop here and not have it keep reacting, we need one equivalent. Because if you remember, this OH2 plus can get protonated. This can come back, kick this out, and then you would get this weird ketonium type intermediate where we have that's not benzene. And then your nucleophile attacks again and kicks back up, and that's how you get the acetal. So we need one equivalent of this for it to work, and that looks like this to me. I don't even know what these are. We'd have to look at them and draw those structures out, but they're not the ring that we need. So none of these look correct to me. We know that we need this nucleophile, so that's how I got here. Now the 2 moles, if we kept reacting, it would end up with a full acetal formed, which looks like this. If you remember the 2 OR groups. I don't know if that's supposed to be a 6-membered ring, but it looks kind of crazy. Might be 7. So we end up with this if we react with excess. So to make it stop, we'd have to be really specific about using one equivalent. So this gets into, I think, chapter 16 with reactions of carbonyls. And this is an oxygen nucleophile. Okay. And then I already accidentally answered 45. How would it be different if we use excess alcohol instead? Okay, 46. What reagents are needed to carry out this inversion shown? Hopefully by now you remember. The thing that I've told you over and over is, what is this called? And y'all always want to call it. This is for my fall 2024 class. Always wants to call this an enamine, because they like how this sounds. But this is not an enamine. A nitrogen with a double bond to a carbon is called an imine. And these are formed when primary nitrogens react with a carbonyl of some kind. Because they'll keep whatever they're attached to. And then they, so if you have, for example, NH2 and then one R group with a ketone or an aldehyde, you get in with your one R group, you lose those 2 hydrogens and the nitrogen's replaced. And we did the mechanism for this a lot, but you obviously don't need to know the mechanism for this. But this is called an imine. An enamine is when you actually have a secondary, I guess I can draw it separately, is a secondary nitro with 2 R groups, and then this would be positively charged, and so you basically get a base to do an elimination reaction, and so you end up with a double bond 1 away from your main site. So that's an enamine. That's with a secondary amine to make the enamine. A primary amine makes the imine. So when I see a nitrogen double bonded to anything like this, I immediately think this right here probably was, it's always when I put my arm in this one specific way. This right here was probably NH2, and this right here was probably a carbonyl of some kind. So that's what I'm looking for, is a carbonyl. And it looks like it has 1, 2, 3 carbons, and right where the carbonyl was, there's nothing on the other side. There's just a hydrogen there. Yeah, let me erase so you can see. If we cut this right here, we have a hydrogen here, and then 1, 2, 3 carbons. So that's what I'm going to draw, 1, 2, 3 carbons. So this is propane with 3, and it's an aldehyde, so propanal. So it's not an alcohol, so it's definitely not propanol. OL is alcohol. And it's not a ketone, so it's not propanone, so it's just B or E, but we know that this has 1, 2, 3 carbons, so propanal. Okay, so that's the answer choice for that one. What is the predicted product? Oh, here we go. This is a secondary amine. Remember, primary amines have 1 R group and 2 H's. Secondary amines have, secondary amines have 2 R groups and 1 H. And tertiary amines have 3 R groups, and they don't react with carbonyl compounds. So this is secondary, so this makes an enamine. So if it were to have made an imine, hopefully you know that the intermediate with that is the nitrogen double bonded to whatever, like this basically gets replaced with the nitrogen and whatever its R groups are. So there's a 5-membered ring with a carbon and the nitrogen on the other side, carbon double bonded to a nitrogen. And this is positively charged. So, oh, hang on. I might have... a meeting. Hold on just a second. Okay, now. Sorry, it's so annoying to pause this recording. Sorry that I just stopped in the middle, but I don't have a meeting until 2. Okay, so I have time. Okay. So let's see. So this would be your intermediate. This would be like your imine, but because it's positively charged there, it can't stay like that. So you would lose a hydrogen from not on the side that the nitrogen was on, but one of the sides over here. A base would take this, go here, kick that up, and so you'd end up with your enamine. Oh, wait. Your double bonds here, your nitrogen's here, and your nitrogen still has all of its stuff. So it looks something like this. So if you just know that a nitrogen plus a carbonyl result in something like this, either an imine or an enamine, you can get rid of this, this, and this. So now you're stuck with either 1 or 2. And if you know that an enamine, when you have a secondary amine, that there has to be a double bond, because ene means a double bond like alkene and an amine, then you should be able to get to this answer A. Because this one just doesn't have a double bond, so it's not an enamine. This is just a plain old amine. So hopefully that was helpful for you. Sorry I had to pause halfway through that. Okay, the next one, what is the predicted product for this reaction shown? This is a reduction reaction. Whenever I see this NH2, this is called hydrazine. Especially when it's followed by a base, I know that this is a Wolff-Kishner reduction. And basically, what happens is you get it. This is just a primary amine. So this replaces with the nitrogen, and it's still bonded to the NH2. So you get the amine, and then when you react that with the base, it just completely eliminates this. So that leaves us with 1, 2, 3, 4, 5, 6. So it's a hexane of some kind. So there's no alcohol, there's no double bond, there's no double bond, there's no double bond. So the only option is A. This next one, propanol, whenever I see this thiol and rainy nickel, that's the same thing. I always think this is a reduction reaction. So it's going to get rid of whatever thing we started with. So we start with propanol, so that's 3 carbons, 1, 2, 3, with an aldehyde. And then we would get with the thiol, it gives us the rainy nickel. I did this exact reaction several times in class, and I think it was even on your last test. So you get this, and then with the rainy nickel, it just completely gets rid of it, and so answer is E. This question was also, I did this a few times in class, and it was also on your last test, so hopefully, if you don't remember, you can see where I solved those in class. But basically, this would, this is just the reaction of carboxylic acid, where this comes up, and you get O-. This is a nucleophilic addition, you get this thing here, looks like that. And then your Cl, and then this comes back down and kicks out, and you get O, and then the base scavenges. This would have been protonated. Base scavenges it, but basically you end up with this. And so that's answer choice A. So this is just converting an acid chloride to an ester. So that's from chapter 17. Okay. This is a Bayer-Villiger oxidation, and it's MCPBA does one of two things. If you have an alkene, it will turn it into an epoxide. If you have a carbonyl, it will insert oxygen on one side of the carbonyl or the other. And you have to learn the migratory aptitude. Like H is the one that's easiest to move, and then I think it's phenol. I don't remember all of them off the top of my head. So I'm not going to write them all out for you, but you should know them before your final. But on this, I know that H is the easiest one to move, so I know immediately that the oxygen is going to insert on the side of the H because it's the smallest, easiest to move. So that's not right. It doesn't insert on both sides. It just inserts on one side. So just from knowing that, I can get to answer choice A. Okay, so the next question, KMNO4 does all kinds of stuff with alkenes. It will cleave them and turn them into, if it has a hydrogen, it'll turn it into a carboxylic acid. But if it's an R group, it just cleaves it and adds an oxygen, just like ozone. So that would do that, where it cleaves right here. There's no hydrogen to turn into a carboxylic acid, so it just stops at the ketone. What would be the major product of the following reaction sequence? PCC would turn this into a ketone. That's an oxidation reaction. We've talked about that a few times already in this. And then the next is LDA. LDA is lithium diamine, which I think, I almost just wrote LAH, but LDA is different than that. This is what we did at the very end, where LDA is a bulky base, and so it's actually going to take the nucleophile. It's basically acts like tert butoxide, where it'll take the nucleophile and leave a lone pair behind. And this makes our enolate ion. And then if you add that with this CH2, CH3Br, that will attack and kick out, and you get this structure, which is an alkylated, you get alkylation at the alpha carbon. So we did this in our last notes packet, second to last, actually, notes packet on enols and enolates. That's where we talked about this. Actually, it might be third to last. It was like chapter 17, I think. Not sure. Where we talked about that. So first we did enols and enolates, and then we did condensation reactions, and then we did amines. And so we talked about this one in the enols and enolates chapter. Okay, so the right answer for that one would be C. And if this happens on your final where it's just like these, that would be A is 1, B is 2, C is 3, you know. So just, you know what to bubble it in. Okay, draw the enol form of cyclohexanone. So cyclohexanone is cyclohexane. It looks like this. And then for a ketone, we get rid of the E. Hexane, we get rid of the E, and it becomes -one. So cyclohexanone is this, where we just added a cyclohexane. And then the enol form of that would be, looks like that. So the ketone looks like that, and the enol has an ene for a double bond and an OL for the alcohol. So ene means double bond, and OL means alcohol. Okay, next question. What product would result from the Claisen condensation carried out with an equal molar mixture of these two things? Okay, well, first of all, let's remember that a Claisen condensation always makes a beta ketoester. And let's see, ethyl acetate and ethyl propanoate. Ethyl propanoate. I probably won't give you a question where you have to know the names of these, because I changed up after I didn't teach you that as much. Ethyl acetate is so it has 2 carbons, and then the oxygen, And then I think it looks like this after. And then propanoate would be ethyl, and then 1, 2, 3. So this is just the common name. So I don't think I'd give you a question like that where I mix the common name and this together. I think this is what it would be. So if you remember what happens with a Claisen condensation, first we get the Enol form, and it can attack and kick up and give O minus. And then, actually, you know what? For some reason, my brain is pausing on this, and I don't want to teach you wrong. There shouldn't be a question like this on your final, so I'm going to pause on this, and I don't know why my brain is not functioning, and I don't want to teach you the wrong thing. I think your final focus is primarily on, do you know that it makes a beta ketoester and what a beta ketoester is? And all of these are esters, where at the alpha beta carbon you have a ketone. So any of these are potential answers, but let me come back to that after. I feel like my brain just paused. And if this ever happens to you on the exam where you're like, for some reason, my brain is not working on this right now, do what I'm doing, pause, and then come back to it. So I put down what I definitely know, and then I'm going to pause, and I'm going to come back to it. Okay, the next one, what is the predicted product of the reaction shown? So this H2 with nickel, we learned a long time ago in OChem 1, it doesn't get rid of double bonds in an aromatic ring, but it can get rid of double bonds in an isolated alkene off to the side. So it would get rid of that alkene. But the other thing it can do that we just learned in this chapter is it can turn nitro groups into NH2. And so it would both eliminate this and it would turn this into an NH2. So what we're looking for is to make sure it switches to the amine. So here it switched to amine, here it switched to amine. This one, it stayed nitro. This one, it stayed nitro. This one, it stayed nitro. So none of those will work. So it's just one of these two. And so I'm choosing answer choice B. Because it also can eliminate the alkene here. Okay, next question. Considering only the highlighted hydrogens, list the following compounds in order of decreasing acidity. So it says highlighted, but what it means is like only the drawn in hydrogen. So like this hydrogen, this hydrogen, this hydrogen, this hydrogen, and this hydrogen. So I believe you'll have a pKa table on your final. I'm pretty sure I put one in there. So that will help you some part of the way where you can know that, the pKa of this is 4 to 5. The pKa of this is 25, and the pKa of this is 16 to 18. The pKa of this we talked about in class is 19 to 20, and the pKa of this is 9 to 10. So these we talked about in class. I don't know if they will be on your pKa table. And we talked about when we went over the enols and enolates how this is acidic, and if it's between two, it's even more acidic. So based on that ranking, decreasing acidity. So the most acidic is going to be the carboxylic acid right here, 4 to 5. So if you can know that, you can eliminate anything that doesn't start with 4. So we get it down to either C or D. Both of those start with 4. And then the next thing they have is either 1 or 5. So do you know that this is more acidic than this? If yes, then you can answer choice C would be right, because 1, and then the next is 3, which is 16 to 18, and then the next is 2, 19 to 20, and then the least is 25. And if you don't 100% know that, even if you don't remember what the pKa of that one is, for example, this has 3, the alcohol being the least acidic. So if you just can check your pKa table and know this and this, that alcohols are more acidic than alkynes, then you could still get to the right answer. So that's how I would encourage you to think about that. Okay, the next one, this is when I see a benzene ring like this with a methyl right here and 3 hydrogens. We learned a specific reaction with I2 and NaOH that is called the haloform reaction. This is an easy way to make benzoic acid and a haloform. So it makes HC and then whatever your halogen is, 3. And so the way it does that is first you get the, your methyl gets 1 halogen, so I'll just use X for halogen. And then it easily continues to halogenate. We went over the mechanism of this at the end of the last class, I think the last class on Friday morning of that day. And so once you get this, this becomes a good leaving group, and so your OH minus can come and attack, and it'll eventually kick that out, and you get your OH and then your CX3, and then your CX3, a lot of times you'll add acid to turn that into HCX3. So that's what I'm looking for here is a carboxylic acid, and there's only one that turns into a carboxylic acid. So you'd get this product plus HCI3. Okay, 59. Which of these choices is a secondary amine? So, let's see. Remember for amines, a primary amine has 1 H and, 1 R and 2 H's. That's primary. A secondary amine has 2 R's and 1 H, and a tertiary has 3 R's. So we're looking for an amine that has only 1 hydrogen off of it. So this has 2 hydrogens, so that's wrong. This has 1 hydrogen, so that's a good option. This has no hydrogens off of it, just carbon, so that's wrong. This is positively charged, so this is like an ammonium ion. And then this has 2 hydrogens, so that's probably also primary. So I think this is answer choice B, but just to make sure, I'm going to draw it out. NH, CH2, CH2, CH3, 2. CH2, CH3. So, yep, looks like this. So that is a secondary amine. So answer choice B is right. 60, what is the predicted product of the reaction shown below? So we talked about how if you have an amine as a nucleophile, it can act in an SN2 reaction, and you will get at least this product. But if you also have this present, it can attack again, and then you would get this here and then your methyl. It's honestly not the best way, and this would be replaced. It's honestly not the best way to make amines because it will overreact, so you kind of get a mixture of a lot of different products. But I think what this one was going for is that you will probably get at least this, where you have the chain you started with, a CH2, CH3 here, and a CH3 here. You would probably get you wouldn't lose your ethyl, so you would not get this because you'd get the reaction with ethyl first. If you added the ethyl first, you probably would get some of this as well. And unless you did one equivalent of this and excess of your amine, which is probably the only way that you could get this reaction to work, and that's probably what they're assuming. You wouldn't get any of this because you've lost the thing that you started with, so that wouldn't work. And same thing here, you've lost the thing you started with. So I think it could be a mixture of 1 and 3, but assuming that they did one equivalent of this with excess of your product, then you're going to try to substitute each one time. So that's how I got to answer choice A. Okay, this next one, this looks like a Gabriel synthesis to me. And this is another way to make amines that we talked about. I said, remember, recognize this and know that it will make a primary amine. And so that's the test question that you're going to have is like, do you know that this is going to make a primary amine, or can you recognize what's going to be made with this? So again, I made this before I went over it in class, so I don't think you need to know this. But essentially what happens is this goes in minus, and then this attacks here and kicks this out, and then 1, 2, 3, 4. So you'd get this structure within, and And then 1, 2, 3, 4, right? Carbon 1, 2, 3, and 4. And then you can use these next two steps right here will essentially release that and give you your NH2 with 1, 2, 3, 4. So this would be your product. So let's count 1, 2, 3, 4. So this is probably the right answer. This is only 1, 2, 3, so that's not right. This is 1, 2, 3, 4, but you should have 2 OHs there, which I'm not going to test you on. This would be an intermediate, so this would form, but it would not be what you get in the end. And then this right here, you're not going to get the NH2s because when it releases, it basically it uses the amide as a leaving group and replaces it with the OH. So, I don't have any idea how I just highlighted it. But I don't think I'm going to make you know, like, I don't think the test question I put in here on this, at least for this semester, for fall of 2024, I don't think I'm going to test you in depth on this. Like, do you need to know what's left behind? Because we kind of ran out of time. So just know that made a primary amine when reacting with this is the biggest thing. Okay. So now let's go back to the Claisen condensation because I got a little flustered on that and I took a break from it. And so I want to go back and think about that one a little bit more. Again, I don't think that the test question I have on that is very complicated. I think it's pretty simple for this semester again because we ran out of time. Which question was that? And I think it more is just asking about, do you know that you're going to get a beta ketoester of some kind? And both of these are ethyl acetate and ethyl propanoate. So I'm just going to look real quick and make sure. I don't want to lead you astray. My instinct is that ethyl acetate is this, and ethyl propanoate is this. And for a Claisen condensation, it's very similar to an aldol condensation, where at your alpha carbon, you'll get this. This is not a great question because either one of these could be the one that attacks. And this would kick up and you would get O. And then this right here is the one that forms a bond to here. And then we go back to O minus. And you have this still, and you still have this, and then this would recover. I think this side would recover and kick out, and so you'd end up with this. Oh. And that's why I don't think this is a great question, is I think you could end up with a mixture. So, and maybe maybe that's the answer. Maybe it's all these choices. But so I don't love this question. So I'm going to just say don't worry about it too much, but make sure you know that a Claisen condensation does make a beta ketoester. And I think that is about as far as we got in this chapter. So I wouldn't worry about that one too much. Okay. I think that is everything. Yep. I think we covered it all. So hopefully that was helpful to y'all for this quiz. And please feel free to comment if you have any questions or email me. And good luck studying.